Hello everyone, this is Mrinal Kanti Roy Choudhury. The title of the talk is Quantization Dimensions of Self-Similar Measures and an Open Question. Let D denote a metric on Rk induced by norm this, and let Sj, where j equal to 1, 2, 3 up to n, be a set of contractive similarity mappings on Rk. That means this relationship is true for all j 1, 2, 3 up to n. Let the set of similarity mappings Sj satisfy the open set condition. This is also well known in any fractal geometry book. That means this relationship is true. Let P1, P2, dotted up to Pn be a probability vector. So when you say this is a probability vector, remember these entries are, each of them are positive and sum is 1. Let mu equal to this. Then mu is a unique Borel probability measure on Rk, which has support the attractor or the invariant set A of the contractive similarity mappings Sj. When you say mappings Sj, that means all of the mappings, that is S1, S2, S3 up to Sn. That is, A satisfies the following invariance relationship, this one. So this A, which is the attractor of the similarity mappings, is the support of the self-similar measure mu. Sometimes A is referred to as the self-similar set, corresponding to the set of contractive similarity mappings Sj. Now, let R be a positive real number and kappa R is this, be such that this. Remember, when kappa R is a positive, it satisfies this relationship. That means kappa R is unique, for which this is true. It is easy to see that there exists a unique real number D, which is non-negative. Also, this is true. The number D is called the similarity dimension. Also, you'll get in any fractal geometry book of the similarity mappings Sj. And if the probability vector is equal to this, then dr mu equal to kappa R equal to D. That means quantization dimension of the measure mu does not depend on this R. But when the probability vector is not equal to the similarity, that is this vector, S1 where D is the similarity dimension, is not equal to this, then dr mu equal to kappa R for R belongs to 0, plus infinity. And see that this R means this R that occurs in this relationship. That means this, notice that dr mu kappa R indicates that the quantization dimension dr mu of the self-similar measure mu, when this vector is not equal to S1D, S2D, SND, this vector depends on the real number R, that is dr mu is a function of R. All this you will get in Graf Ludwig's book, Foundation of Quantization for Probability Distributions. Now, Sierpinski triangle and uniform distribution. Let S1, S2, S3 be a set of 3 contractive similarity mappings on R square, equipped with a metric D induced by the Euclidean norm this, such that for all x, y, S1 xy, S2 xy, S3 xy are defined as follows, as it is given here. S1 xy equal half xy, S2 xy half xy plus half, 0, and S3 xy is half x, y plus 1/4, 3 or 5/4. Then the limit set is generated by the iterated function system, this S1, S2, S3, is called the Sierpinski triangle. Define a probability measure P on R square as follows. Then P is a uniform distribution on R square with the support the Sierpinski triangle is, that this is. By this formula, we can easily calculate with respect to the squared Euclidean distance, that is when R equal to 2, the quantization dimension kappa of the uniform distribution P is given by this. Easy. But there is an open problem. Let P be the self-similar measure on the Euclidean space R square, which has support the Sierpinski triangle is. generated by the similarity mappings Sj, that is S1, S2, S3, as defined before, as defined here. The optimal sets of n means and the nth quantization errors for the self-similar measure P are not known yet for all positive integers n. This is a long time well-known open problem. This open problem also indicates that it is easy to calculate the quantization dimension, but extremely difficult to calculate the optimal sets of n means and the corresponding nth quantization errors. I would like to stop here. Before that, of course, I'd like to tell you the references if anyone is interested to know more. Foundations of quantization for probability distributions by Graf and Lutke. There is another paper. The quantization dimension of, this is a book. Here is a paper, the quantization dimension of self-similar probabilities. You will see there are many interesting results about quantization dimension in these two places. Thank you. God bless you.